Hi, and welcome to the fourth webinar of Copernicus, following the module about security and emergency management. We currently have 100 participants, but we believe much more will join in the next minutes. So our agenda for today will start with a presentation from Peter Bunus from Stellar. That will be followed by a Q&A session. Then our second presenter is Taras Matseliuk, CEO of the OptNet Tsar AI. Well, we will give us a presentation of the Tsar AI platform together with his colleague Francisco Gutier. And finally, our last presenter will be Uxue Doneza Oyos, who is a production coordinator for the Copernicus EMS validation service. So Peter, if you can activate your micro and camera, please, and you will be able to start your presentation.
Hello everybody, so it's Peter here. So I guess we are all set up, right? So I just want to ask the technical team if they can confirm me that you can see the presentation. Mariam?
Yeah, sorry, I got a problem with my connection. Sorry, I didn't hear your question. Sorry.
Can you please confirm if the presentation is...
Yeah, it works fine. You can go on.
Okay, thank you very much.
You're welcome.
Hello, everybody. So, ladies and gentlemen, it's a pleasure to be here. And I would like to ask you to please follow me in a very, very short journey of 15 minutes in which I will try to fulfill an almost impossible task of telling you about machine learning and how we use machine learning in connection with satellite image analysis. Because I guess this is why you are here in this course, to learn about satellite image analysis. And as you probably remember from my presentation during the course, we are using satellite image processing in connection with insurance applications. I will forget for the next 15 minutes that I'm an engineer, and I will try to play the role of an insurer. And let me tell you a little bit what an insurer would like to see and what an insurer would expect from a satellite imagery. As you have seen from the module, the very first thing that an insurer needs to do in order to issue an insurance policy, one needs to assess the risk of that particular object that you are insuring or that particular assets that it will be insured. And for this, so we are using satellite imagery. The process of actually assessing the risk, it's called underwriting in insurance. Now, let's suppose that I need to underwrite this particular industrial compound. As you can see, it consists of several industrial buildings. Usually, this is the information that you get from the insurance broker, so that we need to insure, in this particular case, 39 different buildings. But obviously, more we know about that, so we can create a better picture about the status of the asset. We can create a better picture about the potential risks that are in this area. And just by looking at this satellite imagery, so we can very quickly see that, well, that particular building has a damaged roof. And the industrial compound that I'm trying to now to underwrite or to risk assess, yeah, it's dangerously close to some explosion risk areas. So do you see those containers over there? So those containers might explode and might put in danger my asset that I'm trying to insure. So the role of an underwriter is actually to analyze patterns of real-world activity, to uncover any kind of signals of risk, at a property before actually issuing that insurance policy. So what an underwriter does, so it's actually, well, it looks and tries to assess the danger in that particular area. Now, this is not a satellite imagery. This is an aerial imagery. So, but let's use it for diving a little bit deeper for what we are actually looking for. Just by looking at this imagery, so we can quickly see that, well, some of the houses, they do have a pool. Now, pools can be very risky for certain insurance policies. Yeah. So if you have small children in the household, then the pool represents an additional risk. And as an insurer, we would like to know that. In certain cases, the vegetation, it's very close to the buildings. In case of wildfires, so this actually it's an increased risk to the building. And we would like to know that, so if this is the case or not. The roof shape of every building, it tells us quite a long story about the safety of that particular building. For example, in this image, these two roof shapes, they are of a special type called gable. Now, gable roof shape, it's well known that it's not resisting very well to winds, right? Now, if these two houses, they are located in a hurricane alley, when we know that there is a very high probability of strong winds due to tornadoes, then there is also very high probability that these roof shapes will be damaged during an extreme weather condition. And we would like, obviously, to know that. Solar panels, so despite all the benefits that the solar panel can provide, on the other hand, so it can be also a risk of fire because of the short circuits of the electrical wiring, but it's also a risk imposed to the roof because of the mounting, the wiring, so that the roof can leak. So in case of a rain, but also a solar panel is the first thing that will fly off in case of a tornado, and we would like also to know that. Now, as you can see, there is a lot of image processing going on. So in connection with satellite imagery. Yeah, well, this is not known. So because you are encountering AI-based image processing in other applications as well. In the first picture, so you can see that, well, there are applications that they are detecting buildings, specifying bicycles, detecting people, right? AI-based image processing, it's also used for autonomous navigation. If you are driving a Tesla, so the autonomous pilot, so it will certainly use AI-based image processing for the autonomous navigation. We are now incapable of even looking at the picture, so the machine can detect that, classify so who is in the picture. It can recognize your face. It can also recognize if you are smiling or you are grumpy. So it's called sentiment analysis. And you probably know that, so AI, so nowadays, it's in certain cases, it's even better than physicians in detecting early signs of diseases. I would say that they are looking actually for these particular aspects in connection with satellite imagery. We want, first of all, to classify images, right? In the very first example in the image, so you see the image of a cat. Now, if you are presenting that image of a cat to the computer, we would like to know that this is a cat and not a dog, right? And automatically recognize it. Then, also, we would like in certain cases, not only to classify it, but to localize it as well, to indicate exactly in the picture, so where that cat is shown, right? So by showing a bounding box, as you can see it in the second picture. Now, things are not that simple, right? So because the world is full of dogs and cats, yeah, so there are also other type of animals. So, and we need to detect multiple objects inside of a picture. This is the example from the third image that is shown, that we have cats, dogs, and we are classifying them, we are localizing them, But in certain cases, we want to go even further at the pixel level, so to categorize each pixel which are belonging to that particular category. In this case, it's called instance segmentation, so which is actually shown by the last picture. So we are drawing a polygon very precisely around each cat and around each dog, so to actually to show where those animals are located in the picture. Now I know that obviously we cannot detect cat and dogs from satellite imagery, but we do have the possibility of detecting other type of objects. Yeah, I mentioned to you before. So the first picture here, so it shows an example in which we are automatically detecting all the solar panels over a residential area in Florida. As you can see, we are just providing the bounding box. So we are interested in if this house has a solar panel or it doesn't have, right? While in the image from the right, so we are actually doing an image segmentation. So we are clearly defining the contour of the buildings in order to make, for example, an area estimate of the roof. Then later on, so this picture actually can be supplied to a classifier, so that will classify different type of roof shapes. Another classifier can actually go even deeper and classify the material that are on those roof shapes. Now, if we do that at the level of state of Florida, so you can imagine that this is very valuable information for any insurer to know actually what type of roofs, so what type of buildings, so and how those buildings they are constructed over their portfolio over a very large area. Now, in case of natural catastrophe, and this is an example from 2011 in Japan at Minami Sanriku. This is a picture taken near to the epicenter of the earthquake before the event. This is actually a classification and detection of the buildings in that particular area, also before the event. Then the natural catastrophe, the earthquake event, is happening. And in the later stage, so you would like to know actually what was the damage and classify the damage according to their the damage level. So on the last image, so you will see that with red, so we have marked all the complete destruction of the buildings. With yellow, so we have marked all those buildings that have suffered moderate damage, and with green, so they are marked all the buildings that have suffered just slightly damage. And this is done by the computer in a total automatically way. So the AI system is actually trained to recognize different damage levels over the buildings. Why we want to know as an insurer? First of all, so we would like to know, yes, so actually how much claim do we need to pay to the customers? So how much damage we have suffered in our portfolio. And also, when we can see here that the red buildings, they are totally destroyed. Shall we send the claim assessor for those? Probably not. So we should just pay the policy immediately without even actually bothering to send someone actually to look at the damages on site. This is another example that happened recently. So in Beirut, so it was dominating the news a few months ago. And here you can see also the damage map produced by a team from NASA in collaboration with the Earth Observatory of Singapore. Based on the map contained the Copernicus Sentinel data processed by ESA. And so you can see what there is the areas that have been damaged by the explosion. So they are marked with red. This is done at the pixel level, and in this particular example, the analysis has been performed on a synthetic aperture radar type of imagery, not on optical imagery. So you have already learned about that during the course. Now, I would like now to very quickly to place that particular machine learning and AI techniques into the context. As you probably know, there is a whole geospatial intelligence pipeline so that you need to have in order to actually to get to the results. First of all, we have the satellite constellations, right? So that are gathering different type of data, so multispectral, synthetic aperture radar data, so thermal imagery. So this is the data collection part, so the upstream part, right? Then also during the course, so you have learned a lot about the different services that the Copernicus program is providing in actually preparing the data. You have seen that, sometimes the data is cloudy, so there are shadows. There is a need a lot of data processing, so to take place, so actually to prepare the imagery in a certain way that it's suitable for processing. And then it comes the part that I was trying to give you a very short introduction to you today. So the AI and the computer vision part, in which we are taking the more or less the clean images from the data preparation stage, and we are trying to do something with it, right? So to recognize buildings, classify roofs, recognize solar panels, so classify damages after earthquake events, classify damages after explosion events. And this is actually also, I would say it's another data preparation layer. Then obviously that information that you are expecting from that satellite imagery, so you will need to combine it with other type of data. So a lot of insurance data, but also sometimes third-party data like social, political, demographic data. In certain cases, before we actually issuing a policy, so it can happen that we are fusing 50 different data sources in order to classify and to risk assess a certain object or a certain assets that it's on the ground. And then obviously, is the later stage, so you need to actually to prepare actually what is the product, right? So because the insurers, they will not look at very high resolution satellite imagery, no matter how colorful they are, right? So they are issuing policies. And in this case, so what we are interested in is actually to extract all that data from the satellite imagery, to assess the risk, and then based on the risk assessment, to simply price the policy. So at the end of the day, so at the end of this pipeline, so the product, it's nothing else than a very boring home insurance policy that has a price on it. But it went to a long way from the satellite to the insurance policy that many of you so already they have it for your own homes. Now I was pretty much using a lot of buzzwords, right? So everybody now is claiming that we are using AI in connection with that and that, right? And as you probably all know, so artificial intelligence, it's a very broad area, right? So, and it's a branch of computer science that is trying to mimic the intelligence or behavior of the human patterns and humans or any kind of living entity. And then we have a sub-branch of it, so the machine learning, so which is a technique by the computer can learn from data, right? Now, I was telling you that the AI classifier, it's trained to recognize the roof shape, yeah? So which means that we train that particular classifier, so to recognize that particular task. And then we have the neural networks, which is actually a subset of machine learning. And in most of the cases, in the context of satellite image processing, for what we are doing in the insurance sector, we are mostly talking about deep learning network, which are distinguished from the more commonplace single hidden layer neural networks by their depth. So they are layers after layers of processing, of classifying, to which the data must pass in order to process the pattern recognition, right? So we need to recognize the pattern that this is a certain type of roof shape. So I would say that when we are talking about image classification, image recognition in our context, so we are mostly referring to deep learning neural networks. Now, these came in many shapes. So don't worry, I will not go into the details, but I would just like to give you a list of possible object detection and classification algorithms that we are using, right? And there are quite a lot of them. So in each one of them, so actually you can write a PhD thesis. So they are very complex, and there is a lot of research behind it. So these algorithms can be implemented on different AI platforms. You have probably heard about OpenCV, TensorFlow, and so on. I will, as I said, I will not go into the details. Just I wanted to show you so that usually things are not that simple. So usually there is no silver bullet that will classify everything in your satellite imagery. It's case by case. You need to select the best algorithm or the best platform so that will perform for that particular task. And I just wanted to emphasize at the end of my presentation that the AI process, it's actually a very complicated process, and it involves first of all a lot of data processing. You need to collect the data, you need to label the data, sometimes by humans, right? Before the AI actually can recognize roof types, so there were humans actually teaching the AI, so and automatically and manually labeling the data so that we can have that set to train that. Then there is a lot of processing, augmentation, so there are several iterations. Then you need to select the right model for the right task using the right method. You need to train that. And once the training is performed, so you need to validate and analyze the results in several iterations, right? The AI model, so when you write code, for example, it's not that big. So I always said to everybody that doing an AI process or an AI project, it's actually 20% of coding the model, and the rest of 80% is preparing the data. And this is also true for any kind of image classification and recognition that we are doing in the insurance sector. I hope that this very short introduction and very brief and high-level overview introduction gave you a little bit of insight into the machine learning and AI processing in connection with satellite imagery. And I hope that it will give you the incipient actually to study further, so to look deeper into those algorithms. And don't forget, so when you take the journey to the sky and you look down, bend to the earth, then obviously you realize that the single location where we can learn the most about our planet, it's found nowhere on the earth, but high above. And so we have a lot of work to do. So when we are looking back to the earth, and I hope that this presentation will motivate you to study deeper the AI algorithms in connection with satellite imagery.
Thanks a lot for your presentation, Peter. We have now activated the Q&A. So for the participants, you can address every questions you may have to Peter, and we will display them on the screen. So you can start.
Yeah, so the first question is that if we can use AI to assess damage when there is a lot of cloud cover. Well, obviously we cannot use optical imagery, so and I would say image classification and image detection in the classical way. But when there is cloudy, so then obviously we can use synthetic aperture radar, so or SAR interferometry. So for assessing damages after a natural catastrophe event. I'm not aware of the e-cognition, so thank you very much. So probably I will look for it. So we are not using it. So, but thank you very much for the suggestion. So I'm not aware of that. I cannot comment on this. Yeah, so we are mostly working with insurance companies and reinsurers. Currently, we are collaborating with 7 different insurers and reinsurance companies. Oh, that's a very difficult question. So if I suggest any book or exercise to develop more understanding of machine learning, obviously, well, there are many courses on the internet. So there are many AI programs at the universities. So obviously, well, before my recommendation, before you dive into machine learning or AI, so don't forget about the prerequisites. Calculus, algebra, mathematics. It's more complicated than it seems. So nowadays, so that AI it's popularized by the media. So, but in order to actually to do quality AI research and development, so there are many things that could be studied. So I'm afraid that I will not be able to suggest you a book or an exercise. So but I would probably suggest you to look at one of the AI courses provided by Coursera or by Pluralsight. So in this aspect, but don't forget about the prerequisites. The question is that if for the area of America and the Caribbean, it's possible to get the data to work in that particular area. So if I'm correctly understanding your question, so when it comes to Caribbean, so indeed there are certain challenges. Challenges in that sense that usually the houses they are much more closer to each other. So there is not a clear delimitation between buildings, which makes that, well, the AI classifiers and AI detection systems might have problem of correctly classifying damages or correctly classifying different type of buildings or houses. Compared to the North American houses where things are a little bit bigger, so or the distance between the houses there is also bigger. So I would say that it's usually easier to train an AI classifier over those regions. I'm afraid that I'm not qualified enough so to answer this question. So I don't know how we could identify water loss in the pipeline water network in the rural area. Obviously, well, what one can do, so it's actually you can do a moisture analysis. So there are certain aspects of you can actually detect water, but I'm afraid that I cannot answer this question in detail. Yes, of course. So, well, every company, so that actually every big company that cares about risk assessment could use the work that we are performing, right? Another example, probably you have seen that many times during the course. It's actually precision agriculture, so where satellite image processing can be used. And the AI-based image processing in connection with satellite imagery can be used. Then there are for aquaculture, for example, there are transportation applications that could use this type of services. I'm in case that we are interested in AI analysis where I can access the data in the model. Yeah, so well, it's not that you just download the data in the model. One needs to understand that. So it's always the devil is in the details, right? So obviously there are some of the AI models. So they are published, they are described, so they are available. But as I mentioned before, so that the data for those models need to be prepared. The AI model need to be trained, and the results need to be validated. So I would say that it's a more complicated process than just downloading the data and the model. Yes, of course. So AI can actually use in vessel monitoring. So there are several AI systems that are, for example, used in connection with illegal fishing monitoring, or they are used in connection with commercial cargo transportations. And those AI systems are indeed trained to recognize different type of vessels. So including fishing vessels or cargo vessels, yeah, so that can be trained. Of course, that it's weather dependent. So if it's cloudy, so then optical imagery, so it's very difficult to process. Yeah, so yeah, if pool, it's a risk, right? So first of all, so because a lot of fun can happen around the pool, right? And a lot of relaxing, but a lot of accidents can also happen around the pool. And this is a risk for any kind of health insurance that the members of the household have, right? Many of you have small children, so you know that, well, children's and pools simply do not really match from the safety point of view. And that's obviously a risk. And sometimes, yeah, so the policyholders, they forgot to mention that they do have a pool, and which means that there is actually a higher risk for any of the health insurance policies.
Thanks a lot, Peter. If you have any other questions that have not been answered yet, feel free to post them on the forum on Moodle. And now we will give the floor to Taras Matseliuk. So can you?
Thank you very much, everybody.
Yeah, you. Thank you.
Hello, everyone. Good afternoon. I hope you see me and hear me. I'm going to start the presentation now. And let's begin the session. So my name is Taras Matseliuk, and I'm CEO and founder of OpNet. And our company is on a mission to give everyday humans superhuman abilities when processing big data. I will tell you today a story behind our AI platform, which helps humans with rapid all-weather mapping tasks based on medium and high-resolution satellite data. So how does this work? Okay. So contemporary satellites provide us with great sources of data about daily changes to the Earth's surface. But collecting and processing this data is not enough. The real challenge is to assess the risks, recognize affected area, and attribute the damages in a very short time, as close to real time as possible, preferably if we deal with emergency management situations. Try to interpret the image that of Amsterdam, for example, on this picture. How long would it take you to spot all the features and not miss any? Well, this is a mission impossible as we can see it for humans, and this is where the story behind our product and our company begins. I will tell you a little bit to motivate you to follow our path and come up with your ideas and solutions in this space. And this is the purpose of this presentation. So our idea started when we participated in the annual global Code for Code competition organized by IBM, where more than 100,000 developers from all over the world worked on finding solutions for mitigating of natural disaster effects. Our team was among top 10 solutions out of more than 2,500 teams in 2018. But being semi-finalists was still not good enough for us, so inspired by this initial success, we continued improving our solution and our flood mapping product and participated in more competitions globally. So after a lot of trying and a lot of hard work, finally we won. So our first win was floods mapping project, with which we won with Copernicus Masters Emergency Management Challenge of European Commission in the end of 2018. In the course of the following years, from 2018 to 2019, our official IBM Watson X Prize AI team in the AI for Good competition was advanced to the semi-finalist selections, and through hard work of more than 2 years, we managed to beat more than 100 other AI teams in this multi-year competition. So hope you can also do this. The result of this work was the automatic flood mapping system, which works when it rains a lot. So it works through the clouds and it works day or night. So here I would like to show you some examples in comparison of the products that were produced with our platform and the products which were produced by International Disaster Charter for floods in Vietnam. So it was one of the reference cases. The image on the left, the beige image on the left, was produced with very high resolution data from TerraSAR X satellite operated by Airbus Defence and Space of 3 meter per pixel resolution. So it was produced by humans as well. On the right, you see the image produced by our software at that time, so it was 2018, which was using only Sentinel-2 data, which is 15 meter per pixel. So it's 5 times coarser source data. And as you can see, results are matching quite nicely, but AI was able to do much more than humans. So for example, AI managed to detect non-flooded vegetated areas, flooded vegetation, urban flooded and non-flooded areas with ease. Typically, these areas are extremely difficult to detect by humans, and those who have attempted flood mapping exercises in the past know this very well. So we still use, by the way, the model developed in Vietnam for the reference cases. But AI is so this approach is great, but what I would like to zoom in this example is that by the way, we will give you a little demonstration to show you what the tool can do in near real time at the end of the presentation. But what I would like to highlight that most of all, the ability of AI to process very large amount of data. AI can analyze sequences of images instead of one image that humans typically analyze. And this allows to detect many different details, such as seasonal variations to the water levels, being able to detect the naturally inundated areas and non-naturally inundated areas, which other methods would not detect, like the water bodies that we could map with our XAR AI product could be performed with 4-dimensional precision. So not only 3D, but in time, including temporal axis, which would allow to create dynamic baseline water body profiles, which is something that is still not existing today on the regular products that you could see. And I will show it to you as well in the demonstration later. So let's move on. So to summarize, and again, you will see this in the demonstration, but we will, the process works like this. So we get the SAR image time series from the satellites and pre-process them with traditional methods in order to produce calibrated, co-registered, and geo-corrected data stacks. We also call them analysis-ready data cubes. But instead of using humans, we use these highly complex data sets and huge data sets. A single data set could be 40, 50 gigabytes in size, representing only one small area. We give this data to the proprietary unsupervised machine learning processor that our product is using. And often these products consist of 10 more layers. So the product that I will show you in the demonstration consists of 8 layers. And we will show you how these layers could be used for mapping of the ongoing actual floods which are happening now in south of France, near Nice. But before we go to the demo, I wanted to show you the difference between high resolution and very high resolution imagery. Because very high resolution imagery, in this case, this is a reference case which we used in the past for the floods which occurred in Ottawa, in Canada, where we have been using TerraSAR imagery with 3 meters per pixel. And in such an image, you could see that we also detected the very fine changes to the water bodies, flooded areas, including flooded vegetations and non-flooded vegetations. In this case, I also found other objects such as paved roads, parking lots, which you could see in yellow color, and industrial areas. So which come with these detections come for free. But from how the question is not the speed also of detections, but also what is important is to validate and find that the data and predicted data is correct. So how do we do this? Usually this is done with the creation of the ground truth. And in our reference case in Canada, we actually used the mosaic, highly detailed aerial imagery mosaic, which was manually inspected by our analysts, on which we created a mask of flooded and non-flooded areas. Later, this mask was fed into the system, into the platform, and compared with AI inferences at different probability levels. And this allowed us to make the conclusion that our AI platform was performing close to humans in terms of true positives and true negatives, but it had much higher specificity. So the positive prediction value was 30% higher versus humans, who do not have the capability to spend entire lives analyzing a single image that people have to make to cut corners. The resulting maps with floods could be then used with popular databases such as OpenStreetMap. So in this case of Canada, we calculated the intersection of flooded areas with the OpenStreetMap objects and generated the report where we could calculate the number of flooded objects, number of flooded buildings, critical objects of infrastructure, length of flooded roads, etc. To summarize that our AI approach is a little bit not typical of deep learning approaches used by other players in the industry. We've learned from mistakes of others and created a method which we call a hybrid AI system, where humans and AI work concurrently on many problems at the same time, while emphasizing each other's strengths and minimizing weaknesses. As a result, reusable machine knowledge is created by transferring expertise of human experts to the machines. So currently, our company offers 3 products at different technology readiness level. Some of the products are suitable for production deployments. For example, XAR is currently used in pilots and in the development of the Horizon 2020 projects. We participate in the project GoldenEye, where we are applying the innovation to the mining sector. So the most recent project, Monitored AI, which was using the platform in the areas of North Holland and Groningen, where the product was used for mapping of the agriculture activities. And we received very promising results, and currently working on the preparation of the prolonged 2-3 year large-scale pilot covering entire Netherlands, which would be able to produce precise crop classifications and water moisture maps for a large area of the country. So this is the end of the presentation, and let us try to do a quick demonstration through the screen share session. So you probably have, so let me see, it's probably working, right? So you probably heard about the flooding events that occurred in south of France over the weekend, specifically on 2nd and 3rd of October. There was a lot of rainfall in the area. So this is a town called Saint-Martin-Vesubie, the river Vesubie. And we decided to see what we can do and how can we help. So we launched a mapping exercise with our tool and published the results for analysis. So this is the area which probably is the one that you could have seen in the picture before the flood. So this is optical underlying imagery from digital globe. For convenience, I will switch to the open Topo Map, which gives us the name of the place and gives us the footprint of the river and all the roads and buildings that are also known to the system. These buildings also exist in the OpenStreetMaps, for example. And now we will enable this display of the potentially flooded areas. This case is extremely difficult for flood detection because we have to map tiny objects. How tiny, I will tell you. This cross-section of the town is 100 meters, close to 100 meters. For Sentinel-1 resolution, that's about 5 pixels. So that is already quite challenging. And in this mapping exercise, we are using only Sentinel-1 imagery at their native resolutions. The red areas are areas where it is likely that the floods or landslides occurred. So there are changes in the topology in area. And here with the slider, we could see the probability. So if we put the probability to close to 90%, we can be sure that these areas had been impacted. And how impacted? Well, take a look yourself. So this area looks very similar to this particular object. Of course, we don't have ground verification yet, but we have a very high certainty that the landslide that occurred and the flood that occurred here has been picked up by our solution over here. Of course, this is only showing that this is a risky area, and it justifies the acquisition of the commercial imagery with very high resolution, where we could go to 1 meter or 3 meters of resolution and produce higher precision maps. But as the early warning for the rescue fighters, it's already enough to inform them that this road is destroyed or flooded, and there are a couple other areas that have been impacted, so that there should be certain measures taken. By the way, this analysis was produced while it was still raining, because the image from Sentinel-3, so this is actually the backend tool. I can show you some examples. So this is the bucket that we use, the data bucket that our tool has used to display the imagery. And we could see it's sorted by the date. So it was one bucket is from 2nd of October. And these are imagery, by the way, automatically selected by the tool directly from the DIAS databases. So all we need is to specify the task and to specify the products that cover our area, and the analysis would be happening automatically. So I have captured some of my steps that I took during the creation of the tasks. So you could see them here. So the first one was preparation of the analysis data stack based on my selection from the imagery for the date. So I used the the 3rd of October image. It took about 10 minutes to generate the data stacks and another 5 or 10 minutes to produce the analysis with existing analytical knowledge pack. And then the data was published within few minutes to our publishing point, and now you see the data in the GUI. So this concludes the very brief demonstration, and I'm happy to switch to the Q&A session, and hope to hear from you as well. But I would like to open the Q&A session with introduction of a colleague of mine who, like you, was participating in the last Copernicus MOOC, and now he's working for our company. So his name is Francisco Gutierrez, and he would like to give you a couple words from himself about his experience with this product that I just showed you.
Thanks a lot, Taras. We're gonna now launch the Q&A session. Just like before, feel free to ask any question on the chat and we will display it on the screen.
Yes. Thank you, Taras. Hello, everyone. My name is Francisco Gutierrez. I have a PhD in physical geography, and I was a participant in the first Copernicus MOOC, where I learned about the work developed by OPNet in the field of emergency management. As Taras told, I start working with multidisciplinary team of OPNet, and I have been getting deep knowledge of Oakley. Oakley is the backend platform for SAR AI. In this sense, I would like to share my experience as a GIS and remote sensing specialist with the diversity of systems I have been working on, from the commercials to open source, from desktop to the cloud. I think it is interesting to convey the comparative view of these systems with Oakley. So, in summary, with Oakley, you can obtain a fast computation over large areas in few minutes, as Taras showed to us. And it can easily be adapted to any type of projects and innovative analytical development, such as in the ore industry, detection of illegal vessels, risk of forest fires, and the impacts of climate change. So I think is a tool can integrate different components, different from other solutions where you have different components, like in quantum GIS, with different modules to compute these analytical tasks. So with SAR AI, you can run all the steps for get this kind of. Thank you,
Francisco. Thank you very much. So let's try to answer as many questions as possible in the remaining time. So the first question was, what statistical approach? Actually, we use unsupervised machine learning techniques in this case, and the tool allows to have multiple, actually, you could use different methods. The flood detection case, we use Gaussian mixture combined with K-means learning, and this produces fast results. But it's possible to use other clustering methods which take longer time, and they work for more challenging lane classification tasks. But for flood detection, we didn't have to use them. how one would set up a proof of concept mapping exercise for forward conversion areas identified scared sites. Well, you just contact us and we will be happy to talk to you about this. The matter of fact, we are currently working in the similar land classification tasks in agriculture. So doing the proof of concept would be rather interesting for us. Please contact us either through the forum or through the emails provided in the presentation. What's the best spatial resolution of Sentinel images that you have used for mapping flooded areas? Would you recommend some of the satellite data from Sentinel for mapping over bank flow or flooded area along with the medium-sized river with 10 meters? Yes, so that's an excellent situation, excellent situation that I visualized for you. The rivers on this picture are actually about the size that you mentioned, less than 10 meters. They are not even mapped on the official water body map when we checked. There is only open Topo Map which draws the lines where the rivers are. So officially, Sentinel-1 will not be sufficient for this task. I can already tell you this. As you could see, there are only very few spots of the inundated water areas detected. With Sentinel, you can detect objects which are reliably detect objects which are about 3 pixels in size. And that means that about 60 meters, that is the minimum size of Sentinel-1 images objects that you can detect with Sentinel-1. But for detection of the 10-meter, you will need TerraSAR or PAS or radar SAT. So there are a lot of SAR imagery which exist on the commercial market, which will be useful for the detection of this such small. Actually, this is exactly the imagery where we used in Ottawa, which allowed us to detect much smaller details, where we could see per building damages, where we could see bridges, roads destroyed or flooded. So yeah, you will need commercial imagery for this resolution. Next one, please. Usable for pollution, oil spill detection. Oil spill detection, yes, of course. We will see this very well because we see the wave shapes and oil. What happens with the oil when oil is on the surface of the sea? It changes the surface. It becomes almost like mirror-like because of different viscosity. So the oil spills are easily detectable with SAR. Right now, we are working on a project with the European Space Agency. It's a feasibility study in maritime sector where we are developing and making good results with boat detection and maritime activity detection, because SAR is very good in detecting presence of large metallic objects, presence of ice, and also the changes to the water surface, so mapping wakes of the boats and also detecting activity. It would be possible, I believe, also to detect plastic, floating plastic, if the resolution of the imagery is sufficient. In the case of precision agriculture, we only use SAR images in our case. And the reason for that is because we have been working on solutions for farmers in north areas of Europe, which are predominantly covered with the clouds. So optical imagery was simply not suitable. Just to give you an example, because we just submitted the report, where we can tell you with all certainty that in the northern Netherlands, where we had been collecting data for entire year, we only had 5 usable optical images in the entire year, which could be used for agriculture analysis purposes. The rest of the year had a certain amount of clouds, which was really interfering with small field sizes. But by using commercial SAR imagery and combining it with Sentinel, we achieved very good results, both on the large scale, where the gross estimates were only necessary, and also going down to the small field sizes like 100 by 200 meters, which was sufficient. So if you're interested in the results of these projects, please contact us. I will be happy to give you more information about that in one-on-one session. Do you see it utilized to predict high air pollution levels? Oh, the methods will definitely be suitable, but our current platform at the moment does not support it. Although we are very excited about the possibility to add new satellite data sources from Sentinel-2 P, for example, and the future missions, which would be targeting the aerosol mapping. As you know, SAR is suitable for detecting the presence of water column and pollution particles. So, for example, like mapping volcanic clouds and mapping the pollutant clouds might be possible. So this is an interesting and intriguing area which warrants further research, and we are eager to collaborate, especially if you have in mind the public project or running project or preparing for the Horizon project. We will be eager to participate in this. This is a very intriguing area. Thank you. Yes, the topography is actually part of the solution. It's one of the bends. Actually, it is necessary. Before you can work with SAR data, you really need to have a digital elevation map. This is how we calibrate and prepare the data for analysis by normalizing it. Then the data is being applied to the map of the surface using 3D map. And in the case of floods, we are using the digital elevation in order to distinguish between the radio shadow, which is very typical in the mountains, and water, which is well, less typical than the radio shadow. Can you use the same process in flood prediction and also oil spill mapping? So flood prediction is a different topic because it relies on simulation and prior history of floods in a particular area, because it really depends on the underground composition and on the arrangement of the area. So, for example, there are some areas with a lot of caves and underground piping, which takes away the water, and these areas do not flood. At the same time, there are areas which are high in the mountains, but they don't have any drainage, and they flood easily. So yes, this is an interesting topic to collaborate in prediction, and we have partners with whom we are thinking about it, but these are totally different skill sets. So our skill set is detection and real-time reflection of what's happening, sort of a digital mirror of the real world. And prediction process involves simulation and long-term data series analysis. But both methods can be indeed used simultaneously. About oil spill mapping, I already answered this question. The answer to it is yes. Next one, please, or we are running out of time.
Thanks a lot, Taras. We run out of the questions, so now it's time for us to have our last presentation.
Thank you, Marion. Pleasure to be here.
Have a nice evening. Bye.
Nice evening to everyone. Bye-bye.
So, Uxue, you can now activate your microphone and your camera, please, and we will display your presentation. Uxue, I don't know if you can hear me, but to activate your microphone and your camera, you just have to click on the two icons. Yeah, I see that it's loading. Okay. Yeah, we can hear you.
I'm sorry, Marion. My computer is not very good. I'm sorry.
Yeah, okay, that's no problem.
Hello, everyone. So, hello everyone, I'm Ushua Donezar. I'm currently the production coordinator of the Copernicus Emergency Management Service, Validation Service. And I'm here to talk to you about, about the job we do at the Copernicus EMS, and specifically the one we are doing in the frame of the validation. And of course, the applicability of Sentinel-1 and 2 in this, in our project. So, the Copernicus Emergency Management Service, it's a service that supports all actors involved in the management of natural or man-made disasters by providing geospatial data and images for informed decision-making. It's composed by two components, on-demand mapping and early warning and monitoring. In on-demand mapping, we find rapid mapping and risk and recovery mapping. They provide with cartographic products, both raster and vector, in rapid mapping in the early moments after a disaster has happened, while risk and recovery mapping it creates products that can assist in the recovery of a certain area after a disaster has happened, or can give reference products to help managers to take measures in potential events. Early warning and monitoring, it's composed by three systems, and the goal is to monitor potential disasters related to flood, to forest fire, and to drought. EFAS, the European Flood Awareness System, is close to public, and the information it cannot be consulted, but the other two, yes. And then we have the validation, which is before, up until now, it was within the mapping component, and now it's gone out, and we are also studying sometimes products created by EFAS and EFIS. Our main goal is the validation of rapid mapping and risk and recovery mapping products. In the next slide, I'm going to show you some examples of the rapid mapping and risk and recovery products. I don't know if any of you have tried to see to check the web, but I think it's worth the effort, because the service providers are doing an amazing job, and they are really doing very, very nice products. And here in the slide, we can see two rapid mapping products. One is a fire delineation in Spain. I must say that there are a lot of products related to fire and to floods in Europe. The other one, the one in the middle, in the center, it's a set of products that were created after the explosion in Beirut. And unlike the ones that presented Peter, these ones were made by photo interpretation of satellite imagery. And the last one is the monitorization of ground deformation in a mine in Ukraine, in Solotvinon. This is the following up of a previous risk and recovery mapping activation that I think it was created 3 years ago. I think they do a great job. I am in charge of the technical management of the Copernicus validation service, and I know they are doing a great job. And it's worth the effort to see first the web, where you could see all the products, and then here the activations.emergency.copernicus.eu. Yeah, you can see the viewer with all the activations. I think it's all the activations that they have created so far available. So it's really nice. Regarding our job as the validators, what we do is we provide analysis on demand and assess the Copernicus EMS mapping outputs. Also, as I said before, the early warning outputs. And we are framed in the continuous improvement of the service. We are activated on demand by the Joint Research Center, and we can be activated when the Joint Research Center decides that a product didn't achieve the expected quality. It could also be because the authorized user expressed some disappointment with the product. And it could also be because the activation, the rapid mapping or the risk and recovery activation was especially significant, as it could be after the monitoring of the recovery of IT, what we did, that we did 3 or 4 years ago. And so that's the scope of the validation. In this scope, we do the following activities. First, we have the quality checks and technical validation, which is more the numerical validation, how well the products are. But we also do carry out field data collection. We test new data sources and methodologies that could be applied in the frame of the Copernicus CMS mapping. We test new products as well. We provide with expert advice and recommendations to the service. We compare alternative data sources, and we also collect feedback from users that can be from user feedback forms or from interviews, and carry out impact analysis. What we have to bear in mind always is that the products of the Copernicus CMS, of course, they have to achieve a certain range of quality, which they do. But the most important thing is to create products, to have products that are fit for the purpose. That's why we focus on the feedback collection as well. Sometimes it's not only having a very good product. Sometimes the goal is to have a product which is created as fast as possible. So in the scope of the validation, the quality checks and technical validation, which is a great part of our job, it's we have quantitative analysis of the quality of the product. What we do is we create reference data, the reference crisis information, and we validate the product. Or we reprocess the data created by the service providers, and we carry out a consistency analysis. We create reference data whenever the data available, the satellite imagery available, are of better quality or maybe better spatial resolution. Maybe they were acquired in a more important moment of the event. When we have this situation, we can create reference data and we can carry out a thematic validation. Otherwise, we create the reprocessed. We take the images used to create the product and we make the crisis information based on those images, and we carry out a consistency analysis. And even more, sometimes we carry out a qualitative analysis of the products, bearing always in mind that what it should be, that the focus should be on the usability of the product. Another one of the checks that we usually do is the positional accuracy of the image used to create the product, which I think that people with a remote sensing background will be familiar with. What we measure is we measure on ground the distance between the image used to create the product and a reference image that usually is an orthophoto. Usually, not always. Here in this picture, you can see an example. You see that there was a very noticeable displacement in the y-axis between the image used by the service provider and the orthophoto, and however, the product was considered correct by the users. Other kinds of analysis that we carry out to the products are the prominence of crisis information, whether the crisis information is visible, it's understandable, and the correctness and completeness of the product. If it really has all the information requested by the user, because we should never forget that this is a user-driven service. The appropriateness of the chosen satellite image, whether there was another satellite image more appropriate to create the product, and the topological consistency of the product. Looking back to Tracasa, my company has been in charge of the validation since its creation in 2012. We are now implementing the third framework contract of the validation. And if we look back at these last years, to the last 2 framework contracts, we were activated 52 times. This means we analyzed, the GRC gave us a contract to analyze some products 52 times. In those activations, we created 106 crisis information based on 24 different optical sensors, on 9 different radar sensors, but also based on UAV data, even videos. We also created data based on crowdsourcing data, such as Facebook or Twitter. Also oblique aerial imagery. So any kind of data, we can use it to create our reference information if we believe that its source it's reliable. And in this time, we also made 65 interviews to different users, of which we are very grateful, because without them, we really couldn't do our job. Regarding the Sentinel data, we have used mainly Sentinel-1 and 2 up until now. Maybe in the future we will use Sentinel-3, I'm not sure of that. We have found more useful for us Sentinel-1 data up until now, SAR data. Why? Because it's very good. As I said before, one of the main events covered by the mapping service is floods. And we all know that SAR works very well with floods. We have created crisis information related to floods using only post-event images based on the intensity. As you see here in the left, those black areas are water. Or we have taken advantage of the high temporal resolution of the Sentinel-1 data to create flood information based on pre- and post-event images. This allowed us to automatically discard permanent water or the water that was before the event, because sometimes we face this problem, that is, we don't really know, because we are required to create flood delineation. But if you want to create flood delineation, you have to skip the permanent water. And sometimes in some areas of the world, it's not that easy to have permanent water information of good quality. We have also used Sentinel-1 data for other kind of applications, mainly based on coherence-based crisis information. For those who are not aware, who don't know about the coherence, SAR coherence, SAR coherence is based on the fact that it measures the change between two images, two SAR images, the change in texture in the land, So when we acquire an image just before an event, a disaster happens, and then we are able to acquire an image just after the event, and this is thanks to the temporal resolution of Sentinel-1 data, we can infer that changes in the land have been due to the event. Otherwise, if we took the images very far away from each other, the changes could be related to any other kind of changes. With this approach, we have created crisis information related to floods, in a long-lasting flood caused by El Niño. We have also created fire delineation data. Here you can see how this area in yellow is really giving us the delineation of the fire. And we also applied the very same approach to create data related to lava flow. Here in this image, this green area is the lava flow of a volcano. I think that in this sense, Sentinel-1 has proved to be very, very useful for emergency management. Okay, as for Sentinel-2 data, we have mainly used it for fire delineation and fire severity classification. Why? Because its spatial resolution is a limitation for us. However, its radiometrically, its spectral resolution, it's really an advantage for fire delineation, because it allows us to calculate vegetation indices that are different from the typical ones that only use the near infrared and the red. such as the burnt area index. With a Sentinel-2, we can calculate normalized burnt ratio, and having the pre-event and the post-event image, we can calculate the differential in between both ratios, and with that make a classification of fire severity into destroyed, damaged, and possibly damaged categories. Also, here in the left, you can see the delineation of fire that really it's very straightforward with Sentinel-2, sometimes more than with other sensors. To my experience, if you want to delineate forest fires and you are not going to count for every burned tree, I'd rather take an image of a Sentinel-2 image rather than a Pleiades. Why? Because what I lose in the spatial resolution, I gain it with the spectral one. And now, just to finish, some research lines within our validation service. As I said before, we also are committed to propose improvements and propose other data sources or other techniques that could be applied in the Copernicus EMS mapping component. So we have been working lately, we have been working in the creation of decision trees for the optimization of areas of interest for the Copernicus EMS products related to floods. So we can automatically discard areas that cannot be flooded or that are not prone to be flooded, such as a mountain. And in this way, optimize the area of interest of the product. We have also assessed the influence of the number of control points and the acquisition method, manual versus automatic, for the positional accuracy assessment. We have analyzed the building damage assessment based on satellite versus based on aerial imagery, because to our experience, the damage assessment to buildings based on satellite imagery tends to underestimate damage. Even if the product is usable, it tends to underestimate it. And we have also studied the applicability of Sentinel-1 for landslide detection and delineation. And just to an end, some of the research lines that we are carrying out in Tracasa outside the validation, but that could be in the future applied in validation or in the Copernicus EMS mapping. We are working on the super resolution of Sentinel-2 images, Sentinel-2 10-meter bands to 2.5 meters. This is a very interesting project, and that could overcome the limitation of the spatial resolution of Sentinel-2. Here you see on the left, you can see the original image, while on the right we can see the super resolved image. This process should not be compared to a resampling or to a pan-sharpening, and it's based on the bands themselves, and we have created it. We have created it after a long study, and it really gives us 2.5 meters Sentinel-2 images without significantly varying the radiometry of the image. And finally, other research lines that we will apply in the validation in the future, hopefully, is the segmentation of roads using Sentinel-2 images and the segmentation of buildings to use it in the damage assessment to buildings. And this is all from my side. Thank you for your attention. If you have any doubts, I will be glad to answer your questions. Also, you can contact me by LinkedIn. So, any questions? I think that was a question for Taras. Well, we usually, for positional accuracy assessment, we acquire them manually. We have also used in the past field data collection. We went on field to Sweden, and we we took control points on field, but we usually make it manually. What we are investigating now currently is the difference between manual and automatic acquisition, whether it could be somehow automatized. Up until now, our results show that if while the image is not very bad, doesn't have a very low, very high acquisition angle, or the area is mountainous and very complicated, the automatic approach works quite well. Best. Thank you. Okay, for flood, we have mainly used Snap, but this was made on purpose because we wanted in the beginning. You have to understand that we started to work with Sentinel-1 as long as it was released. So we in our first moments we wanted to test how far could we go with Sentinel-1 and with Snap, which is a free software. And because we wanted to test the free software capabilities, at the moment we are also using NV for SARC processing. And what would be the best solution? Sentinel products related to floods the best resolution would be the spatial resolution of Sentinel-1 images, which is approximately 10 to 14 meters. I think we have used it more than maybe 80% of the times. Because you have there's something that has happened with SAR data. We are now very used to having it because we have Sentinel-1 data, and that is very nice. But I've been working in remote sensing for 15 years now. And up until now, SAR data wasn't so available. We have used also Cosmo, and we have used RadarSat and TerraSAR, but they are not so easy to find. And you have to take into consideration that we always have to use the image that is acquired in the precise moment of the flood. And for instance, with Cosmo, it's very, you can find easily Cosmo images in Italy because they have an arrangement, but Cosmo is not that easy to be found. It's not easy that Cosmo is looking at the place that we wanted to look at. So yeah, 80% Sentinel-1, yeah. Well, it's actually not, we have done studies, and because the purpose was, of course, not to affect the spectral resolution of the bands. And our studies show that, I don't know the percentage of the change, but the changes are not significant, which means the super resolved bands could be used to derive vegetation indices, for instance. Thank you very much, Marco. Enjoy being here.
Thanks a lot, Uxue.
Thank you.
And thanks a lot to our presenters today. If you have any other questions, don't hesitate to post them on the forum on Moodle. And we hope you enjoyed the webinar and that we will see you next week for the 5th module, that is resource management, sorry. And